ladies and gentlemen. My name is Schäfer. I have been working for 2.5 years at the Department for Fluid Mechanics and Aerodynamics. It is in Darmstadt, in Germany. My tasks are developing and optimizing of optical measurement systems for particle characterization. And today I'm going to talk about time shift technique for measurement of size and velocity of particles. Okay, here's the content of my presentation. Firstly, I will give motivation, the historical background of the measurement technique presented here. Secondly, I will present some basics regarding time shift technique. Then I will show how the velocity and the particle size can be calculated. And subsequently, I will discuss instrumental design and show you some experimental measurement results. Let's go with motivation. If you have a look at this table, you see here different measurement principles with corresponding measurement techniques. And this is, as you can see, we have different measurement techniques for characterization of particles and spray. And today I'm going to talk about time shift technique. Time shift technique was first introduced by and more widely by Tropea, and the first results and ideas are summarized in these three publications. And that was the crucial questions why we need the time shift technique. And at this point, I would like to say only two crucial advantages of this system. Firstly, this measurement system can be operated in backscatter. In backscatter configuration, it means it means the detector and the light source are on the one side. And the second advantage is it has simple instrumental configuration. Okay, let's start with the basic. What's the time shift technique is, how it's works. The time shift technique based on the light scattering on the shaped light beam. We have the shaped light beam here, and the shaped light beam should be smaller, must be smaller than the particle size. If the particles moves through the shaped light beam, the light scattering takes place. And the scattered intensity can be measured by a photo detector in backscatter configuration. It's depicted here. In the backscatter, you have typically second order refraction and reflection, whereas reflection exists for each scattering angle. Okay, let's look in details how the light scattering takes place. If the particles passes through that shaded light beam, at first the surface wave will be emitted. Secondly, the reflection takes place, and subsequently 2 modes of second order refraction there, as you can see, and which are followed by surface short path. As you can see, the particle transforms the beam in space into a time signal, and we are calling the signal time shift signal. Especially here you can see that in time shift signal you can separate different scattering orders and their mode in time. As you can see here, this is for example 2 modes of second order refraction, and this is reflection. Everybody can hear me? Yeah. It's okay?
Load up, please.
Good. Okay. Let's look now the basic principle and experimental setup of the time shift. At least one light source and one photo detector is required. The light source, the light is focused by a simple cylindrical lens to some light sheet and parameters of typical parameters, and the scattered light will be detected by a photo detector. And the optical system before the detector and the light sheet define the measurement volume in this system, which are typical 1 cubic millimeter, but you can change it. If you have a look in this picture, you see the typical time shift signal, measure typical time shift signal from diesel particle. You can see 2 modes of second order refraction here, and reflection peak, and as well as a surface wave. We neglect the effect of surface wave because the intensity of this surface wave much lower than the intensity of reflection of other scattering orders. Okay, let's look. We have now the time shift signal. We know how it's works, but now is the crucial question: how we can use this time shift signal to calculate velocity in the particle size. Okay, at first we have the time shift signal. You see here, this is ideal time shift signal, and you have two modes of second order refraction and reflection. You have the information. At first, you have the information, the time distances between these peaks. The time distances between these peaks can be calculated by using ray tracing method, taking into account the velocity of the particles and the particle size. Yeah, and you can describe using geometrical optics basic approach. And you see here, this is these time distances are given by these equations. This function depends only on refractive index, scattering angle, which are assumed to be known parameter in this case. Okay, the second important point here, you see this time shift distances depend linearly on the particle size and the velocity. It means you have here the problem. If you want to use this time distance to calculate the particle size, you must know the velocity. Okay, we calculate also the velocity from the time shift technique, and we taking the advantage of the fact that the individual and the width of the individual heat is related to the beam shape, to the size of the light source, of the light beam, and to the velocity. It means we can use this simple relation to calculate velocity. V is the size of illuminated light beam, and sigma is the width of the signal, also the size of individual peak, we can say, in time. Okay, if the velocity is known, you can calculate the particle size. This is basic things. Okay, and now, if you're going to characterize the particles in sprays, you have several problems must be solved. At first, you have first problem that more than one particle passes through your measurement volume, and this is the biggest problem. As a result, you have then some overlapping time shifts. What cannot be used for analyzing and to provide the necessary information. It means we need some validation principle, and this validation principle should be based in physics and not on some measurements principles. And we're calling this validation principle gamma validation. The gamma, this is the gamma, and the gamma is given as a time ratio between these peaks and these peaks. Yeah, here, as you can see in this equation. Each time distance depends on velocity and the particle size, but the time ratio between these peaks doesn't depend on the velocity and the particle size. This is what we need if we are going to characterize the particles in a spray. This is important. And as you can see, the gamma can be written as a function of scattering angle and refractive index. And here's some numerical calculation of gamma. Gamma, here is depicted gamma as a function of scattering angle for different refractive indexes. And the most important point here, the gamma is a bijective function. Okay? Bijective function means for given scattering angle for one scattering angle and for one refractive index, only one gamma is clear. This is bijective function. Okay, you have this diagram, and you can use this validation principle to validate the time shift signals. And first, so let's take you have ethanol spray, typical case, and you have scattering angle 158 degrees, yeah? And it means the theoretical value of gamma should be equal to. It means you are looking for each signal, and if the signal doesn't have the value of the gamma equal to, you should reject the signal. Okay, let's summarize how we calculate and how we use this gamma validation of this slide. Okay, you have time shift signal, typical from photomultiplier. Good, you have given parameter by experimental setup, refractive index, scattering angle, and the thickness of the light beam. Okay, from refractive index, by given refractive index, scattering angle, you can calculate the gamma. Okay, this is the theoretical value of gamma. Then after signal processing you can calculate the time distances between peaks as well as the width of individual peaks. And from time distances you can calculate the experimental value of gamma. And the next step, what you are doing, this gamma validation principle, what you should do, just if experimental value and theoretical value of gamma is approximately equal, you can use this time shift signal for signal processing. And you can use this equation to calculate velocity of the particle size. Okay, let's speak about instrumental design and limitation of the time shift technique. First, I'm discussing here the limitation given by physics, by light scattering effects. And first, for the time shift technique presented here, you need reflection and 2 modes of second order refraction. Reflection exists for every scattering angle in backscatter, but the second order refraction exists only for angles which are larger than the first main rainbow indicated here. You have also the case for smaller refractive indexes and smaller scattering angles, that the third order refraction, second order refraction are overlapped, what is not desirable. It means the scattering angle should be also larger than the second main rainbow. And then you have also 2 cases where you have only 1 mode of second order refraction and where you have 3 modes of second order refraction. This is also not useful region in this diagram. Okay, as a result you have this region of diagram where you can operate the time shift technique for characterization of transparent particles. Okay, let's begin. You have, for example, in scattering angle, refractive index 1.34, and you can operate this system. You can use this system for scattering angle between 140 degrees and 160 degrees. Okay, it was the limitation given by refractive index scattering angle. Now let's speak about limitation given by particle size and beam size. If you have a look at these 2 pictures, you see here some overlapped time shift signal, and here some not overlapped time shift signal. Overlapping of time shift signal takes place because the particle is too small compared to the beam width of the light sheet, as you can see. And you can characterize this effect by this ratio. This is the particle size divided by the beam width. In order to analyze this mathematically, you have your 2 necessary conditions. Then after some mathematical manipulation, you will get some results like this. Here you see the ratio, the minimal particle size being detected divided by the width of the light beam as a function of scattering angle calculate for different refractive index and also polarization of the light. As you can see in this diagram, as exists for one refractive index, it means for one material, exists one optimal scattering angle, where you have the best time resolution. Okay, let's present me experimental results. At first, just some basics. This is schematical illustration of experimental setup. Basic, light source, 2 photodetector, spray. Here's this nozzle. Here's the nozzle. It's not depicted in the picture. Then there's some typical parameter of experimental setups. Angle 135 degrees. And then as a measurement, in this case, I measure the fallen glass particles. And from different height, I have here the nozzle and measure then the fallen glass particles, and I vary the height. And the typical time shift signal of glass particles, for example, looks like this measured signal. Actually, you see here 2 signals. This is one signal of this detector, and this is the second signal of this detector. Yeah. You have 2 signals, you have 2 information more. and it is also good to define measurement for this technological problem, what I'm using two detectors. I'm not. Okay, you see here, this is some basic experimental setup, also photomultiplier, some lens, laser diode, photomultiplier, whatever. Good. And glass particles, as you see, the glass, here the glass particles, and this is the distribution of the glass particles measured by imaging method, for example, taking photograph. And you can also see that these particles are not perfect spheres and whatever. And let's look to the measurement. In this movie, you see here is just time shift signal. Illustrate the time shift signal, and here corresponding particle size distribution, velocity distribution. You see this. I plotted here. I show here the first 500 measurement points. This is the time shift signal depicted, and here the particle size distribution, velocity distribution. This system is real time. Good. Let's look the results. As I already said, the distance between nozzle and the measurement volume was varied. I used here the different distances, 10 centimeter to 60 centimeter, and these different measurements. You see that these measurements are highly repeatable, and this gray line indicate the distribution of the particle size measured by imaging method. It means this is the true particle size. And also from velocity distribution you can see typical physical behavior of falling glass particles. I'm not going to discuss it, it's not interesting. Good, now it's the end of maybe my presentation, but after discussion with some person here, I found maybe I can explain a little bit more what we are doing actually. At first, we have been developing time shift technique not for characterization of transparent particles. For characterization of transparent particles, we have the best system, PDA, PDI, but we have been developing this system for characterization of suspensions and non-transparent particles, as well as of some extraordinary particles and so on. And you see here, this is a measurement of milk particles. Here's the basic principle. You have some milk particles and you have some small particles inside of these milk particles. You measure also, you have here two detectors, and you have two physical effects. The first effect is reflection on the surface, and the second effect is the reflection inside, reflection on this particle, on these small particles, which are inside of this big particle. As a result, you have the typical time shift signal for suspensions. This is what we're calling this baseline, and these two peaks are just corresponding to the reflection effect. And you can use, we have some model, and we can then calculate the particle size and the velocity of the signal, and this is also some measurement, yes, and not very interesting. And here is our results: particle size distribution, velocity distribution. We measure milk spray operated. We measured milk spray created by a flat fan nozzle from company Lechla, aperture around 1 millimeter maybe, and operated by 2 bar, and here's results: particle size distribution, velocity distribution. Okay, maybe it's all, but maybe we can use this time shift technique for measure refractive index. It's very interesting. It's very interesting because you don't need to change on the side of the detector. You don't need to change your setup. What you have to change on software side, how you interpret this signal, how you use, and whatever, which model do you use for analyzing signals. Okay, let's discuss refractive index measurement. It's just not refractive index measurement, it's just better to say estimation of refractive index. Good. If you have two time shift signals, two detectors, you have two time shift signals. It's like this. One signal is mirror of another. Yeah? And then you can, okay, and here typical parameter of my measurement setup. It's nothing changing, just getting angle 155, and I measure sprays created by flat fan nozzle operated by 2 bar in different liquids: water glycerin, ethanol. I need to look for different liquids. Good. Let's look. at first, clear, we found also a new validation principle, how we can validate two signals, not each signal, individual signal, but also both signals. We're calling this validation beta. You have here this same situation like in gamma validation principle. I'm not going to discuss it. It's not interesting, and this is the idea. You have here measurement setup. You have here this typical time shift signal. You are doing several steps, analyzing of signal, and you are getting this result. And as you can see, this is the result. Here, this axis indicates relative refractive index, and this is distribution. And you see each curve in each curve it's around 5,000 points. And you see here I can distinguish between water and ethanol, maybe water and glycerin, and maybe I can also I can distinguish also in spray between water and ice particles. I looked at yesterday for refractive index of these objects. It may be interesting, but you see the problem is here. It's not precisely, but maybe it's technological problem. Maybe if we can analyze the signals better, it's getting better. But we are from a department for mechanical engineering. We concentrate just on the important parts. And we are going to present our experimental setup, a HEMA method exhibition, and it takes place in June in Frankfurt. This big exhibition, I don't know, maybe 10,000 visitors. I don't know. You can look this at Google, HEMA 2012. Maybe if somebody go to this exhibition, they can visit us. Okay, conclusion. Also, this work was founded through Deutsche Forschungsgemeinschaft. Also, and here the steps. What I'm going to do is clear. We want to develop some commercial device. It must be small, I don't know. It must be small. And the second, what we want to do is just we want this in developing this system for agriculture. It must be very cheap. Okay, thank you for analyzing in spray in agriculture. Thank you very much for attention, and I'm waiting for questions.
Thank you for your presentation. Are there some questions about this talk? There are no questions? Maybe I have one question. What will be the minimum size you can detect with the time shift technique?
The minimal size which can be detected?
It depends on the beam diameter.
Yeah, on the beam diameter, yeah. And the minimal beam diameter which I could create in my lab was 10 micrometer.
So I think you're 20, 30 microns.
Yeah, maybe, but anyway, yeah, like this. And this is as I already said, it's useful maybe for characterization and sprays of sprays in agriculture.
Yes, these are
Yes, this is the reason. And you have their larger particles in agriculture. The most important point is mass flow, and the mass flow depends on larger particles.
So we will now other questions? Yes.
What is the size of the measuring volume? Is it comparable to a phase Doppler, larger, smaller?
The size of the measurement volume, especially in this case, is 1 cubic millimeter. Because you define the size of measurement volume by aperture before detector and lens system. And you can play, and it depends on situation what you want to have. Because bigger aperture is good, more intensity.
How you're measuring the velocity by the full width, half maximum height. How clean does your beam profile have to be to get this done?
This is for example in this case you see this is the time shift signal, and my beam profile of the light source I can optimize very well.
You must do that.
Yes, I must knew that. I said in this step. Maybe I didn't say it really. You must know the size, and this is also the biggest problem of this system. But anyway, as I already say, it is not a system for characterization of transparent particles, because we have phase droplet. This is the base system, clear. We're using this for characterization of suspensions, non-transparent particles.
Thank you very much.
Thank you. Now we come to the next presentation. It's droplet sizing errors in interferometric spray measurement techniques.